So today I'll be presenting my algorithms for nanoindentation strain rate jump tests. And I'll get started by discussing why we care about the strain rate dependence of materials. So for the last long time, we've been able to measure the strain rate dependence of large, for instance, tensile specimens, where if we look at the high strain rate behavior, such as almost 1 per second, we can see that it requires a lot of stress in order to deform the material. And then if we go to lower and lower strain rates, we see that the stress required is significantly less, and we get more and more deformability. And you can see from the citation that this is at least from the 60s that people have done this. But the issue with doing tests like this is that we have very large scale specimens, so we don't have any site specificity in measurement of mechanical properties. So in the last 20 years or so, we've moved to microscale testing using uniaxial compression of things like micropillars, where we can do the same types of experiments. So this is 5 × 10⁻⁴. The material deforms mostly homogeneously, and we see that if we increase that strain rate even 2 orders of magnitude, still within the quasi-static regime, that same material in the same phase starts to crumble. So we can see that as we change our strain rate, the deformation morphology can change, and that's probably due to the change in underlying deformation mechanism. However, we don't always want to be making micropillars because it takes a very long time to create micropillars. It takes additional time to test them. So sometimes it is preferable to be able to infer the dominant mechanism by measuring physical parameters. So what physical parameters can we measure? How do we quantify the strain rate dependence of these materials? Well, we can do that in 2 ways. We can do that with M, which is the strain rate sensitivity, and that's looking at how the log of the yield stress changes as a function of the log of the applied strain rate. There's a secondary parameter called the activation volume, which is more intrinsic to the deformation process. And that's also related to how that yield stress changes as the applied strain rate is changed. And so these two can be combined, and different thermally activated mechanisms have distinct M and V star values. So particular to things like BCC materials that have that deform primarily by thermally activated mechanisms. For instance, very low V star values can indicate things like kink pair mechanisms. Very high activation volumes can indicate dislocation interactions. And those are just a few examples. But like I said, we don't necessarily want to do micropillar testing all the time. So we can turn to nanoindentation. So I'll briefly go into nanoindentation and some of the analysis. So we take our probe attached to our transducer, and we're indenting the sample secured to the stage. And all of the work shown here will be using the Bruker probe, which is one of the standard probes in our lineup. And it's a 3-sided pyramidal indenter. So as we indent the sample, we load the sample, and we measure simultaneously the load and displacement on the sample, both during loading and unloading. And we can calculate the unloading stiffness from the unloading portion. And this is where the important properties come from, where we're measuring the reduced modulus based on the stiffness in the contact area, and the hardness based on our maximum load and our contact area. So that contact area, as a reminder, is the projected contact area of the indenter during the indentation process. And that's evaluated at our contact depth, HC, which is actually related to the maximum contact depth minus this epsilon term the maximum load over our stiffness. So it's important that we be able to accurately measure this unloading stiffness, because this stiffness gives us our contact depth, which gives us our contact area, which gives us both of our desired property measurements of modulus and hardness. And so we can extend that a little bit further and do multiple unloading cycles, such as on this partial load unload type load function, and that gives us properties at discrete depths. So each one of these unloads is giving one of these hardness versus contact depth points. And we can extend that one step further to what is called the continuous stiffness measurement, or in the Bruker line of products, continuous measurement of X, or CMX, using the nano-DMA technology, where we're applying an oscillatory load on top of our applied quasi-static load. And that's giving a near continuous measurement of, or a near continuous unloading, giving us high depth fidelity and depth dependence of properties. So because we're going to need to measure the strain rate dependence of these, we're going to need to define what the strain rate of these of Berkovich indentation is. So for self-similar indenters like the Berkovich indenter, our strain rate is defined as h dot over h, which is the displacement rate divided by the current displacement. We're going to be doing these all in load control, so we need to write this a little bit differently, which is equal to 1/2 p dot over p minus h dot over h, where this p dot is the loading rate divided by the current load minus the change in hardness over the current hardness. And we can approximate this as 1/2 p dot over p. This comes out to be an exponential function in terms of time. So for a given constant strain rate, we get the exponential curve seen here. So we can do this in series, where we apply one p dot over p, change to another p dot over p, and so on, and measure the corresponding change in hardness due to each one of those jumps. And that is what a strain rate jump test is. And so we can measure these same properties. We can get V star and M, and instead of looking at the yield stress, we're now looking at how the hardness is changing as a function of our strain rate. And so the way that I've developed these algorithms is that we have 3 pieces of software that are going to be used in series. The first one is a Python script that takes our inputs, such as the applied strain rates, the loads that we're going to change those strain rates at, and the oscillation frequency and oscillation amplitude, just to name a few. And we put these into our code that gives us the load function that is loaded into Triboscan. Triboscan is going to tell the instrument to run those indentations. It's going to give us our experimental data in the form of a text file, and all of the analysis functions are then written in MATLAB. So one problem that we have, though, is that we need these input parameters that we put into the load function to get into the same analysis, because we need to know, for instance, when those strain rates were changed and what strain rates those are. And so this creates a second file called the parameters file, or the PRM, so that we can get these inputs into our analysis. And then the analysis is going to give us, among others, it's going to give us the strain rate sensitivity, M, and activation volume. So all of these functions are freely available on GitHub at the